Hello, welcome back. In this video we'll discuss the surface to volume ratio. While discussing the nanoscale, we have said that the nanomaterials they behave entirely differently when compared with their bulk form. That is, the nanomaterials are expected to have a different set of physical and chemical properties when compared to their larger form or the bulk form of the same material. We have also seen various reasons using which one can explain the deviation in the physical properties from the bulk materials. The first reason we have discussed was the nanomaterials have a relatively larger surface area when compared to the same volume or mass of the material taken in the larger form. We have seen the example of 1 gram gold in its bulk form and 1 gram gold nanoparticles. We have said these two materials they behave differently and they will have different set of physical and chemical properties. The main reason for this could be due to the increased surface area to volume ratio in the case of nanoparticles. Suppose you have a material in the form of a sphere whose radius is say r units. Now what is its surface area? Surface area of a sphere is known to us, it is 4 pi r square. And what is the volume? The volume of the sphere is also known to us, it is 4/3 pi r cube. Now if you take the ratio of surface area to the volume, surface area to its volume, we get 4 pi r square upon 4/3 pi r cube, or the ratio will be 3/r. Since r is known to us, that is the radius of the sphere, if r is increased, we see that the ratio between the surface area to its volume becomes smaller, and when r is reduced, the ratio increases quite fastly. And this ratio plays a major role in deciding the physical and chemical properties of the matter. Let us look at another example. In this, we have a cube of 1 centimeter. The side of the cube is 1 centimeter. You also have a cube of 2 centimeter side and also a cube of 4 centimeter side. We have three cubes. One is having 1 centimeter side. In the second cube, we have 2 centimeters, and in the third cube, we have the 4 centimeters. Now, area of the side of one side of the cube will be 1 centimeter square. And for a cube there will be 6 such surfaces, so 6 centimeter square will be the surface area of the cube, and the volume of the cube will be a centimeter cube, and the ratio of surface area to volume is 6/1. And when you take a 2 centimeter cube, the surface area of one face will be equal to 4 centimeter square. A cube has 6 faces, so you get 24 centimeter square. Volume of the cube is 8 centimeter cube, so you get 24/8, that is 3. That is the ratio of surface area to volume, which is equal to 3 in this case. Similarly, if you look at the 4 centimeter cube, the side of the cube is 4 centimeters. Area of one side of the cube is 16 centimeters, and there are 6 such faces. So the area is 96 square centimeters, and the volume is 64 centimeter cube, and the ratio is 96/64, which is 3/2, that is 1.5. What we understand from this discussion is, as the side of the cube is decreasing, the ratio of the surface area to volume is increasing. For a cube of a centimeter, we see it is 6. And for a cube of 4 centimeter side, it is 1.5. The ratio can be maximized when you take a smaller piece of the material, or when the material is taken in a smaller size. The size that we talk about is the nanoscale. So when you take the material in the form of a nanomaterial, then we'll have the physical properties and chemical properties that are going to be different. This is how the surface area plays a major role in nanomaterials. In this video, we have started our discussion with an example of a sphere, and we have said that the surface area to its volume is 3/r. And similarly, we have also discussed another example where 3 cubes are taken, and we have seen that the smaller cube has a greater ratio of surface area to volume. Thank you.